Hi, good day everyone. My name is Firdaus. Today I'll be presenting the very large scale integration VLSI tutorial number 2. Now, our group consists of 3 persons, that is myself, Ahmad Firdaus, Om Prakash, and Abdul Fattah. We have divided this tutorial 2 into 5 parts. That is the first part, the Jupyter notebook execution. The second part is the PMOS and NMOS FET connected up as an inverter. The third one is extraction, the gate capacitance and junction capacitance. The fourth part is the forward and reverse current voltage, characteristic and effective resistance. And the fifth part, that is development of a digital circuit of single inverter driving 4 inverters. That is also known as fan-out 4. Okay, part 1, the Jupyter Notebook execution on MOSFET simulation. So this is the code that we've run in Google Colab. We have come out and we've got the result as in the snapshot here. You guys can see the image. That is the NMOS. So NMOS stands for N-channel metal oxide semiconductor. The pink color here represent the conductive channel, which is formed when the voltage is applied to the gate, allowing current to flow between the drain and the source. The green area here, on the other hand, is doped with donor atoms, the N-type. And they are separated by the channel. The black background represents the substrate or the body of the transistor, that is the P-type for the NMOS. Okay, just a note here that the actual color used in the diagram is arbitrary and is meant to visually distinguish different parts of the transistor. The actual materials and doping types of the components are what determine their function. Now, this is the image to generated. That is the PMOS. You guys can see here that the PMOS, the pink color here also represent the conductive channel. But in the PMOS, this channel is created when a negative voltage is applied to the gate. The green areas in the context represent the source and the drain regions doped with acceptor atoms, the p-type, and they are also separated by the channel. The black background signifies the n-type substrate or body of the transistor. And we also have the simulation run, that is this for the NMOS MOSFET. Can see here the curve shape. The graph shows a quadratic relationship that is typical for the NMOS. The current increase with the square of the voltage beyond the threshold. And here is the PMOS MOSFET simulation. So the curve here also similar to the NMOS graph. The current voltage relationship is quadratic. However, for a PMOS, both the voltage and the current are in negative range, reflecting the p-channel operation, where a more negative voltage leads to an increase in the absolute value of the current. Now, we've come to the part 2, that is the PMOS and NMOS FET connected up as an inverter. This is how it looks in the code that we've run after that in the Google Colab. So this inverter circuit is a basic building block in digital electronics, also known as a NOT gate. The pink color again here in both NMOS and PMOS transistors shows the channels that control the flow of current. The PMOS and NMOS transistors are arranged in such a way that when one is on conducting, the other is off, and meaning not conducting, and vice versa. So the output of the inverter is taken up from the connection point between the MOS and the NMOS and the PMOS, where one of the transistor drain is connected to the other source. When the input is high, the NMOS channel conducts, the PMOS does not, and the output is connected to the ground low. Conversely, the vice versa happened. Okay, we're coming to the part 3, that is the extraction of the gate capacitance and the junction capacitance of NMOS and PMOS for the 130 nanometer process technology. Extracting the gate capacitance, the methods that we've used is that this analysis, the AC analysis, or so-called small signal analysis in the simulation tool that we have performed, where a small AC voltage signal is applied to the gate, and then the resulting AC is measured. So we have applied about 10 millivolt, and the gate capacitance can be calculated with this formula that and then we've come to the junction capacitance extraction. So in this junction capacitance, that can also be obtained through the small signal analysis, whereby we apply the small AC voltage signal between the drain and the source for NMOS or PMOS and measure the AC current. So the junction capacitance is calculated as drain source capacitance junction here with the formula, and where the drain source is the change in the drain. And then this is the result that calculated for the NMOS gate capacitance. We got 50 femtofarad. PMOS gate, we got 60 femtofarad. NMOS junction capacitance, we got 30 femtofarad. PMOS junction capacitance, we got 40 femtofarad. So the implication for circuit design in 130 nanometer process technology in this context, the process this 130 nanometer technology, the capacitance values have several implications for circuit design. We have summarized 6 of them. Number 1 is that the performance optimization. Second is the power consumption. Third is noise margin. Fourth is the sizing transistor. Fifth is the delay consideration. And sixth is the interconnect. Designer must carefully consider these capacitance to optimize circuit's operation and to meet the design specifications. Okay, we've come to the part 4, that is the forward and reverse current voltage characteristic and effective resistance. We have summarized this as follow. So the characteristics, these are the aspects, and we have the forward IV and the reverse, and we have the effective resistance. So these are the description, and these are the transistor types, and these are the behavior in forward direction. It's showing for the forward, increasing gate source voltage leads to increasing drain current in the on state, and on the other hand, the reverse IV, very little to no current flows in the off states. For the resistance part, the effective resistance varies with transistors operating point. So number 4 here, we have the behavior in reverse direction. For the forward IV, we have no significant current flow. For the reverse IV, we have the very little to no current flows in the off states. And for threshold voltage, we have the forward IV, the voltage at which the transistor starts conducting in the forward direction. Number 6, we have the effective resistance. This only applies to the forward IV, where it varies with the operating point, and the effective resistance. This can be estimated from the IV curve. Now the implication here is that for forward IV, the key for transistor operation in the digital circuits. For the reverse IV indicates off-state behavior. For effective resistance, it is a critical delay and speed in the digital logics. Okay, we're coming to the last part, the final part, part 5. The development of digital circuit of single inverter driving 4 inverter. This is also known as fan out of 4. Now we have evaluating the speed and of the inverter using the logical effort method and also the RC time constant method and do the comparison. So this what we have developed the fan out for. So for the logical method, we have taken the physical values for logical effort parameters. That is the intrinsic delay of a single inverter, 10 PS. The fan out F of a single inverter is 4. And then the second part, we have the RC time constant method. This is where we use the existing value of resistance and capacitance that we have run in the program. So the value here is the output load capacitance, CL, 50 femtofarad, effective resistance in driving NMOS 1 kilo ohm, effective resistance of the driving PMOS is 1 kilo ohm. Okay, the comparison is that the logical effort delay T is equal to 2 nanosecond. So the logical effort method provides a more accurate prediction for the inverter performance as it considers the logical effort parameters and fan out, making it a better choice for estimating delay in the complex digital circuits. On the other hand, the RC time constant method is resulting in 0.2. But that's also the real-time scenario that is here. We have taken the initiative to put some chart to compare the RC time constant method with the logical effort. So in real scenario, the delay for each inverter stage may not be the same. Here's an explanation in bullet points. So to illustrate the real scenario with varying delays. Now, stage 1, we have the input inverter. The input inverter which receive the signal may have a logical effort delay of 2 nanoseconds due to its structural and electrical characteristic. But if we move to the right side, we can see that the stage 2 has increased and also the RC time constant has increased. And this reflecting the increase of the capacitance. And stage 3, we can see as well, this increase even further, whereby the logical effort can be seen as 2.8 nanosecond. And the RC time constant is 0.18 nanosecond. So this is due to the cumulative effect of the capacitance from the multiple stages earlier. And stage 4, the final, that is the logical effort of 3 nanoseconds, indicating the slowest response, and as well as the RC time constant has increased up to 0.2. So, well, that's it. That's the real scenario of the delays. That's the end of our tutorial number 2. We'd like to thank everyone. Then if there's any question, you guys can email us or drop a message to our email at UTP address email. That's it. Thank you all. Thank you, everyone.